In this video, we're going to look at solving a few basic limit problems. Now, when we're dealing with a limit of some function, and we're trying to find that limit value, generally the first step is to try and plug your a, the value you're approaching, in. In this situation, if I were to plug 1 in, I would end up with 1 squared minus 1 in the denominator, or I essentially will have 0 in the denominator. So we know we can't plug it in because it will give us an undefined value. Since we can't do that, we have to figure out another way to solve this limit problem. What I would do would be to try and manipulate it algebraically. Now notice, as I'm doing my work, I'm rewriting the limit here. That limit is part of the problem. So essentially, it should be in your work every time you write a new step. So I'm going to look at factoring the numerator. And the numerator is easily factorable. I've got 5x and x. And then I have a 2 and a 1. I'm going to put my 2 over here with the 5 and 1 there. In order to get negative, those will have to both be negative. And then in the denominator, we have x plus 1, x minus 1, because the denominator easily factors as a difference of squares. Now, one thing I would notice, especially since that denominator was so easily factorable, because I know I want something to reduce and cancel out, I get that x minus 1 in the denominator. I'm expecting an x minus 1 in the numerator. Now, it's not always going to be that way, but it's just kind of a hint. I'm looking for something to cancel, so I was expecting that. Anyhow, now that we cancel, that leaves me with the limit as x approaches 1 of 5x minus 2 over x plus 1. At this point, I can take that 1 value and plug that in. So that's 5 times 1 minus 2 over 1 plus 1. Notice, once I reached that step where I was plugging the value into the expression, I no longer write the limit as x approaches 1 in there. So this is going to simplify, and I've got 5 minus 2 over 2, or 3 halves. 3 halves is my solution. It's the limit value of this function as x approaches 1. Let's look at another example. Our next limit example, we're going to be looking at the limit as x approaches 25 for this rational function, the square root of x minus 5 divided by the quantity x minus 25. Immediately, I go and I try to plug the 25 in, but of course that's going to give me 25 minus 25 in the denominator, which means we'll be dividing by 0, and that is not defined. So we have to look at and determine a way to manipulate this so that we can plug that 25 in. Now, this is not quadratic in the denominator, so we can't factor it at all. One thing, and the trick that we like to use, especially when we see these square roots in the problem, is to deal with multiplying by 1. When we multiply by 1, the strategy we like to use is to multiply by the conjugate. And conjugate means that I'm merely going to change the sign in the middle. So this was square root of x minus 5. I'm going to use the conjugate square root of x plus 5. Of course, that's like a difference of squares. We know there's some nice canceling when we multiply two conjugates. All right, now I'm not finished writing what I need to write here because we're not allowed to just multiply by some random number. However, we are allowed to multiply by 1. So I'm going to put that square root of x plus 5 over itself. And now I can FOIL the numerator as well as the denominator. So we'll look at FOILing that numerator. That's going to give me the limit as x approaches 25. Square root of x times the square root of x is the square root of x squared, or just x. We'll have minus 5 root x plus 5 root x, and then negative 5 times positive 5 gives us negative 25. So I still have my denominator, which I haven't multiplied yet, which is x minus 25 and the square root of x plus 5. So one thing, I don't always multiply that denominator initially. And the reason that is because I want this x minus 25 to cancel. So hopefully this magic I performed in the numerator is going to give me something that will let that cancel. Now, the nice thing, again, about multiplying those conjugates is the middle terms evaporate. So I'm left with the limit as x approaches 25 of x minus 25 over the quantity x minus 25 times the square root of x plus 5, all of that in the denominator. And what you see is that x minus 25 over x minus 25 cancels. This leaves us with the limit as x approaches 25. That gives us 1 in the numerator, canceling common factors, so there was still a times 1 there. It is not a 0. And then I have the square root of x plus 5 in the denominator. So now that I've canceled the initial problem factor, it's gone now. Again, I'm going to try and plug that 25 back in. So that's 1 over the square root of 25 plus 5, which we see here simplifies quite nicely to 1 over 5 plus 5, or rather 1/10. So the answer to the original limit problem that we were given up here is 1/10. Let's look at one more limit example, and this is going to be the limit of a piecewise function. In this last example, we are dealing with a piecewise defined function, which has 3 pieces. So f of x is equal to the first piece, x minus 1, on the interval when x is less than 3. F of x is equal to the second piece, 2, constant function, between x equals 3 and x equals 5. And then f of x is equal to the line x plus 3 for all values of x which are greater than 5. Now, of course, we can always begin by creating the graph because the graph gives us something really nice to look at. So x minus 1, and that's going to be on the left or less than x equals 3. So x minus 1 is a line of slope 1 with a y-intercept at negative 1, and it's going to travel about like this. So from x equals 0, negative 1 to that 0.32. And it's an open circle because we are not including 3 in there. So the next piece between x equals 3 and x equals 5, we have the constant function f of x, or y, is equal to 2. So that means we have a horizontal line. And since it can be equal to 2 at both of those boundaries, we can include that. Those are going to be closed dots. And that closed dot is going to fill up the hole we had from where it couldn't equal 3. Now, for our third piece, which exists to the right of x equals 5, we just need to plot a point. So I'm going to start, if I plug in 5, it's a line of slope 1. Plugging in 5, that's going to give me this ordered pair, and it's not to scale up here. And that should be an open dot, but plugging in 5 gave me out the point 8. So I have 5, 8, and it's a line of slope 1, so it's increasing. All right, so looking at this, as x approaches 3 from the left, and as x approaches 3 from the right, we can see what the y value approaches, and we know the answer to this problem is going to be that output 2. Now, if we didn't have the picture, how would we do this algebraically on our paper? I'd say, all right, well, let's talk about the limit as x approaches 3 from the left. And approaching 3 from the left means I'm using the function x minus 1. And if I plug 3 into this function, 3 minus 1 gives me 2. Let's look at the limit on the right. So that's the limit as x approaches 3 from the right. Approaching 3 from the right, our piecewise intervals let us know that that's going to be the constant function 2. And of course, we know the limit of a constant is the constant. And what you see here is that the limit from the left and the limit from the right are the same. Therefore, the limit is 2. Let's do a second problem with this same piecewise function. So if we look at the limit as x approaches 5 of the function f of x, well, what happens at 5? When we come in here and look at 5, we can see that the left and right are not matching up. They're not forming a continuous flowing line. What is the limit as x approaches 5 from the left of the function? Well, approaching 5 from the left means we're using that middle piece, or 2. And the limit of a constant is the constant. Let's look at the other piece. Approaching 5 from the right. Approaching 5 from the right means we're using the green piece. X is greater than 5. So that piece is x plus 3. Plugging that in, I've got 5 plus 3, or 8. Now 2 is not equal to 8. And since the left-hand limit and the right-hand limit do not match, the limit does not exist. And that's our final answer there. So I hope this helps you think about, how to solve these limit problems better. We always want to try and use algebra on our paper, but we do also always have our graphing calculator on hand, so we can look at the graph or create a graph to help us visualize what's going on and figure out how to determine the answer. Please let me know if you have any other questions, because I am here to help.